lift-induced drag. Lift-induced drag, in this case for fixed-wing aircraft, is going to be generated as soon as lift is created for fixed-wing aircraft. For rotorcraft, it's a little bit different. It's as soon as we start having lateral motion. As soon as the drone starts moving sideways, then we start creating induced drag. The interesting thing with induced drag is that, as opposed to the other type of drag that we just looked at, this one decreases as the speed of the aircraft increases, okay? Induced drag decreases as the speed of the aircraft increases. Let's think about this for a second. The greater the angle of attack, the greater the induced drag. Just take this for granted for a second. I'm going to show you how it works with a diagram in a second, but greater the angle of attack, the greater the induced drag. Let's take a look at this. Remember the angle of attack? The difference between the relative wind and the chord line? This is a high angle of attack. This is a lower angle of attack. Now, as we have a higher angle of attack, we have more induced drag. This is what I'm talking about right here. Now, why? Well, let's go ahead and take a look at this diagram right here. We have our RW, relative wind, coming from this direction. Then we have our chord line that's drawn between the two. Now we have a low angle of attack right here. A low angle of attack in most cases means a faster airspeed, all right? Let's take a look at the relationship between all the different vectors. Now notice as we go to medium angle of attack, what we have is an increase in the resultant force. It's more of at an angle, which as a result means that the induced drag also has to increase. Now you notice what I did is I kept the lift, the orange vector, the same because we have to maintain the same altitude here. So we are creating, for the same amount of lift, more resultant force and also more induced drag at a high angle of attack. Let's go to the critical angle of attack right here, very high angle of attack at a much slower speed. And what happens is now you can really see that the induced drag is increasing even more. Now, a high angle of attack means a slower speed. So in this case, remember what I told you in the slide before? I said the slower we go, the more induced drag we have. Actually, what I said is the faster we go, the less induced drag we have, which is the same thing. And the stalls are basically what happens when the airfoil reaches what we call the critical angle of attack. The critical angle of attack. Most aircraft that fly have what's called a stall speed, the speed at which the aircraft is going to stall. Now, when we say stall, a lot of people think the engine stalls. It has nothing to do with the engine, okay? Stalling all has to do with the wing losing lift. We don't have lift generated by the wing anymore. And as you can imagine, if we don't have lift, then we can be in trouble. We don't want this. We don't want this situation. So stall is not something that we want to be in. Now, very interestingly, a stall can happen at any airspeed, but it's usually associated with flying at very low speed. Now, let me explain again. This is our airplane, okay? This is a low angle of attack, right? You guys agree with that? Low angle of attack. As we increase the angle of attack right here, eventually we're going to be at the point where if the airplane is moving still in this direction, this is our relative wind right here, okay, increase the angle of attack. Now the airplane here is slowing down, slowing down, slowing down, slowing down. And as we slow down, we need to create more lift in order to stay up in the air. And as we get to that point here, we reach what's called a critical angle of attack. Now the airflow is going to hit here, but it's not going to stick to the top of the wing right here, which means that we don't have any lift anymore. What's going to happen in most cases is that the nose of the airplane is going to drop. This is where most of the weight of the airplane is because of the engine, so the nose is going to drop like this, okay? So what I said in here is a stall can happen at any airspeed, but it's usually associated with flying at low airspeed, and that's because of this right here. As we get to a very low airspeed, we reach the critical angle of attack, which is the difference between my finger right here, which is the relative wind, and the chord line right here, okay? Now what happens is, the reason I said it can happen at any airspeed, because it's all about that angle. Now if you think about, if the airplane was to fly down like this, okay, you're in a steep descent. which means that the relative wind is not coming from this direction, right? If we go like this and we're in a steep descent, which means the airplane is going pretty fast, and we pull on the control real fast, then we reach, again, that critical angle of attack right here. Even though we're going pretty fast, then we can reach that critical angle of attack and stall the airplane. So stall can happen in really any conditions. In most cases, it's going to be associated with flying slowly, but not always. So what happens during a stall? Because that's something that can get confusing. Now what happens, as I've shown you already, is the airflow is no longer sticking to the top of the wing, which means it's called laminar. It's no longer laminar on top of the wing, which basically stops the lift for a short period. Now, on the fixed wing aircraft, this will result in a nose drop because the nose of the airplane is pretty heavy. Now you're going to say, what happens with a quadcopter? Can a quadcopter stall? Well, not really, because remember, the lift that is being created by your quadcopter is generated by the motors. The lift in a fixed wing aircraft is created by the wing, which is what stalls. It's the wing. So in your case with the quadcopter, very few chances of stalling. I can't even think of a situation where that would happen because the propellers are churning so fast, they're always creating lift. The only way to recover from a stall when you're in a fixed wing aircraft, and you could be flying one of those with a little remote control, then is to lower the nose of the airplane. You have to reduce the critical angle of attack back to a regular angle of attack. Here's what happens. Here's what the airflow looks like compared to the relative wind. That's normal condition right here, very low angle of attack. As we start increasing the angle of attack, the airflow sticks to the top and to the bottom of the wing. And as we get to the critical angle of attack, then the airflow is disrupted, no longer laminar on top of the wing, which means that this is what we get. We basically have loss of lift. We lose that lower pressure at the top, which means that we no longer have lift. Roller coaster, and you're getting to the top. Related to all of this is what we call the load factor. Now the load factor is a representation of the acceleration of gravity. What does that mean? Think about being in a roller coaster and you're getting to the top of the roller coaster, and then all of a sudden it goes down, 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 and then all of a sudden as you get to the bottom it goes up again, and then all of a sudden you're pushed down on your seat, you're stuck to your seat. Well, this is what load factor is. It's the acceleration of gravity. You've heard it with the term G-forces, okay? G-forces, that's what the load factor is. Also, sometimes it's called the resultant load, and I'll show you in a diagram in a second. Interestingly, the load factor is going to increase with the bank angle of the aircraft, which means that if you have a fixed wing aircraft like this and you bank, which means turning like this a lot, and you maintain altitude, you're going to put a lot of load on the wing. Now, why is this important? Well, go back to the roller coaster idea, where you're going down, 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 and then all of a sudden pull to go back up, then you're getting squished into your seat. That force right here that your body feels is the weight of your body multiplied by the load factor, the number of times that you're increasing the gravity by. This airplane right here can only withhold so much load factor. So as we go down, 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 and then pull on the control real hard, then all of a sudden if we pull too much, then see these things right here that are holding the wings together, it can come off, and then all of a sudden we destroyed a wing on the airplane. There's unfortunately an accident as I'm recording this a couple weeks ago of an airplane that disintegrated in flight because of this. Too much load putting on the airplane and tried to recover at the last minute and pulled too hard on the control, and the airplane just came apart. So those are unfortunate. This could happen, especially with a small model airplane made of balsa, and then you just pull too hard, and then the airplane, the wings could just collapse, basically just fold right here on the top. Here's a picture representation of the load factor. What you notice is the different terms. What we have is for the lift The lift is not only always going to be perpendicular to the relative wind, it's also going to be perpendicular to the wings right here. So as we start banking, then our lift is also going to be created like it is on the diagram right here on the left side. We have a vertical component of the lift and a horizontal component of the lift. And then opposite to all of this, we always have opposite forces, and we have weight. As long as the weight is equal to the vertical component of the lift, then what we have is we have level flight. We're not climbing, we're not descending, we're maintaining altitude. And then what we have is, if we have the centrifugal force, which is the horizontal component of the weight, if you want to call it that, of the load, then if the centrifugal force and the horizontal component of the lift are the same, the opposite forces are the same, then we're established into a nice little turn like this. And then what we have is the load is going to be equal to the lift. So as much lift as we create is going to be the amount of load that we're going to feel in our seat as we're doing the turn. Now, in this case, because it's a model airplane, then it's the amount of load that the airplane is going to feel on the wings, and that the wings need to be able to sustain. Just as an example, a 60-degree turn, like you can see on the right side of this diagram right here, a 60-degree bank like this is going to be 2 G's, 2 times the force of gravity, which means that if this airplane was to weigh 10 pounds, then all of a sudden, with the bank angle, then that airplane is going to weight the equivalent of 20 pounds, which means that these wings have to be able to support the 20-pound weight that is being put on by the force of gravity. This diagram right here is showing you the relationship between the bank angle at the bottom and the load factor on the side. What you see right here is, for example, for a bank angle of 60 degrees, we have a load factor of 2 times the gravity. And you can see the table on the left side showing you the same thing as you'll find on the curve. If you go to a bank angle of 85 degrees, which is almost a 90-degree bank angle right there, you're at 12 times, 11.5 times the force of gravity, okay? This is huge. Even at 80 degrees of bank, it's going to be 5.7, almost 6 times the weight of gravity. So obviously it's exponential. The more you bank, the more you're putting strain on to your aircraft. To affect the stall speed of the aircraft. Remember, we talked about stalls and we said when you reach the stall speed of the aircraft. Remember, we talked about stalls and we said when you reach the critical angle of attack, typically it's when you get to a certain airspeed. And in this case, because of the load factor, that speed is going to change. And this is also extremely important. Load factor, the more load factor you have, the faster you're going to stall, the sooner you're going to stall. And I'm going to give you an example in a second. This is important because as you get closer to a landing, if you fly one of these, as you get closer to a landing, then you're going to be flying at a slower speed because you don't want to be landing at a really fast speed on that runway. So as you come in closer and you fly at a slower speed, if you start doing abrupt maneuvers that increases the load factor, then all of a sudden your stall speed is going to increase. I'm going to give you an example. If you were to fly, okay, you're flying around, and let's say that you're coming in at 20 miles an hour because that's what your UAS is designed to do. You're coming at 20 miles an hour, but you know from the manufacturer that 15 miles an hour is your stall speed, okay? 20 miles an hour, you're flying, everything is good, you're still 5 knots over, or 5 miles an hour over the stall speed. If you slow down too much, if you slow down to 15, then the wing doesn't have enough to create lift, it's going to stall. Now, you realize that something is going on the runway, you can't land there, and you start to do a 60-degree bank. And as you do a 60-degree bank, what happens to your load factor? Load factor is 2, and that load factor is going to affect your stall speed, and it's going to increase your stall speed. Your stall speed that was 15 miles an hour could be 25 miles an hour all of a sudden. Remember, you're only flying at 20, so now you're 5 miles slower than the stall speed. boom, you stall the aircraft. Just because you banked on final, just because you made a sharp bank to avoid something, now you stalled and boom, here goes your UAS. This is actually something that kills people in real airplane, in manned aircraft, because you're flying pretty slow, close to the ground, and if you do an abrupt maneuver to avoid something, then you can go into a stall and then not be able to recover. So something to remember. This can happen really, it happens to people. They lose their UAS all the time at flying field because they do this kind of stuff. But here is a diagram to kind of give you an idea of how much it increases your stall speed. On the left side, it shows the increase in stall speed, and then on the right side, it shows your bank angle at the bottom. So let's take a look at this example here. If we had a 45-degree bank, a 45-degree bank means that our stall speed increases by 20%. Our stall speed increases by 20%. So if our stall speed was 20 miles an hour and we did a 45-degree turn, now 20% more than 20, that's 24. Now we stall at 24 miles an hour instead of 20 miles an hour. Okay? So like my example from before, we would be really, really close. We were flying at 25 miles an hour. Stall speed is now 24. We have 1 mile an hour margin, so not really all that much. I know I gave you a lot of numbers in this video, so if this is unclear, please let me know, but I want you to really understand how all of these terms are related, how load factor changes your stall speed, and how it actually changes the G-forces, which is how much the aircraft is going to have to sustain in order to fly around. So load factor is an important term in this case. Next concept I want to talk about is called stability. And stability is important because it's the ability of the aircraft to return to the original flight path after being disturbed. Let's take the example of the quadcopter, okay? If we were to put the quadcopter into a right turn like this, all right? Right turn from my view. Right turn right here. And as we do this, as we go to the right turn, if we let the flight controls go, and if that drone were to continue going into this right turn, then that wouldn't be too good, right? What we want is we want that drone to do this, and then as we let the controls go, it goes back to normal. That's stability, the ability of the aircraft to return to the flight path. Same thing if we were to go on a climb. As we stop climbing, then we want it to stop after a while or immediately, depending on how stable it is. That's again called stability. There's two different types of stability. The first one is called static stability, and the second one is called dynamic stability. Let's go ahead and talk about both of those. Static stability is the initial tendency to go back to equilibrium. Initial is the key word right here. Let's think about this for a second. Here's our airplane right here, and as the airplane is being put away from equilibrium, okay, so I pull on the control on my remote control, and it goes up. Then what I want is I want it to go back to equilibrium. If the initial tendency is for the aircraft to go back to where it was before, then that's good. That's positive static stability. If my aircraft is going to do the same thing, go back down, go back up, go back down, and do this forever, it's going to be neutral. Now, if as soon as I let go of the control, that thing goes up, and then all of a sudden it actually stops, and it keeps getting worse and worse and worse. If I pull on the control, and then all of a sudden it's going to go up, up, and actually it gets worse after I let the controls go, it's going to be negative static stability. Again, this is the initial tendency. So the example that we have here is what you'll find in the PHAC in your pilot handbook of aeronautical knowledge. And what you'll see is that if I were to disturb this, let's say a cup, okay, we have a solo cup on top of a table, and we initially just put a force onto it. If it eventually rocks and goes back to the original position, then it's positive static stability. If we have that cup on its side and I start pushing it, and if there was no friction on that table, it would just keep on going. Okay, go into it. It would never go back to the original position, but it wouldn't get worse. So that's neutral static stability. And finally, the last one is if I push my cup when it's on its back, and then I push it, and then it never goes back to the original position, then it's negative static stability, initial tendency, as opposed to the other one, which would be dynamic stability, which is the aircraft's response over time when it is disturbed. Now there's 3 different types as well. However, this gets a little confusing because the first one is a positive static and also a positive dynamic. Everything we're going to look at is based on the fact that the airplane has a positive static stability at first. Positive static, positive dynamic, what happens is as it is disturbed, over time it's going to go back to the original position. Okay? The next one is positive static but neutral dynamic. What happens is we disturb the aircraft and then it's going to go back down and go back up to the original state, go back down, and it's going to keep on doing that forever. All right, that's positive static, neutral dynamic. And the last one is positive static but negative dynamic, in which case if I disturb the aircraft, then it's going to get worse and worse and worse and worse and worse. All right, positive static, negative dynamic. CG, because we don't need nearly as much tail down force, which means we don't need as much of a pitch up, means that we're going to get better cruising speed. It also means, because of better cruising speed and increased range, we can go further. It means a shorter takeoff distance. On the downside, it means decreased stability, because now our center of gravity and our center of lift are really close to each other. I'm not going to go into detail as to why, but that actually decreases stability and makes it less easily controllable for the airplane. Which also means that on rotation, it would be easy, because a tiny little movement of the tail right here could over control the airplane, which means that on rotation, when we take off, then we could have issues taking off too early, and same thing on landing. This also means a lower stall speed, but I'm not going to explain why, just kind of learn this. This is important if you fly a fixed-wing aircraft. If you fly a rotorcraft, then it's completely out of the window. It's a little bit different. What I want you to remember from this, if you fly a rotorcraft, is the fact that the center of gravity is still going to have an effect on performance for your quadcopter. In terms of a forward CG, when the gap between the CG and the center of lift is bigger, the arm, then we have the opposite of what we had for an aft CG. We have a slower cruise speed, a decreased range, a longer takeoff distance, but on the positive side, we have increased stability. We also have an easier stall recovery. It's going to be harder to flare, but also we have a higher stall speed. So positive and negatives on both sides. It depends on how you load the airplane. Now, remember also that all of this is when we load the center of gravity within limits. We stay within the limits of the center of gravity. So you can't really have any damage done to the airplane by doing this. It's just different types of performance. Center of gravity limits. Those limits are called the envelope. The envelope of the airplane is where you need to stay within. You need to be within the maximum CG location in order for the airplane to be controllable. If you exceed those performance, that envelope, then the airplane will become uncontrollable and will not perform as highlighted by the manufacturer, just like I told you about that accident of that airplane. Too far forward, the airplane will never get off the ground, which means that you have a nose-heavy airplane, which is going to be very hard to get off the ground. If you have the center of gravity too far aft, then what's going to happen is that the airplane is going to stall as soon as it becomes airborne, because you're going to have a tail heavy airplane. In terms of the quadcopter, I want you to think about this a little bit. This is the quadcopter, and obviously because we have 4 motors right here, the center of gravity is going to be right in the middle of these 4 motors. That's where we want it to be, so that when we start lifting up, all we need to do is create forces on all 4 motors, the same forces, in order for the quadcopter to go up. With that being said, what's very important here is if the center of gravity starts moving forward or back on this line right here, then it's going to put more strain on these 2 motors. If we have a nose heavy airplane right here, if this is too heavy, it means that these 2 motors here are going to be working harder. As these 2 motors are working harder, these 2 are not working as hard, which means that these can probably overheat over time, which is not good. If we have a CG that's moved too much on this side, then the opposite is going to be true. So when you load up your camera, if you load up maybe a 3D camera that you want to put in here, a 360 camera, then you have to make sure that the airplane is still going to be balanced correctly. Now, I don't want to do this because I don't want to let it drop on the ground, but the center of gravity for this airplane feels very much like it's right around here. Right around where that dot is right here for the battery, that's pretty much where I feel the center of gravity is located. So when you load something, you want to make sure that it's going to be loaded close to this spot right here. If it's a string, if it's a camera hanging down, if it's going to be too far forward, then it's going to make it nose heavy, and too far back, it's going to be this way. This is not a drone that's designed to carry any kind of payload. You want to do this when you go to the next level with the Matrice, or even the Phantom is going to be pretty hard pressed to carry much of anything. Whatever you do, always make sure that the weight and balance are in limits. In a quadcopter, if you're going to take off, make sure you take off slowly and see what happens. If it's too much weight in the front, then the drone might just tip forward. The propellers will basically go into the dirt or into the concrete, whatever you have here, break your propellers, and then you'll be done for the day. So that's what happens when you exceed CG limits. Side is going to decrease. Now you're going to say, what does that mean? What does that have to do with my performance? Well, the performance of your aircraft is going to be directly related to the pressure outside. As the pressure decreases, the density of the air also changes, and the amount of air that each propeller movement makes is less, which means that the performance is going to decrease. So you have to be careful. Lift is going to be reduced. I flew my drone once at about 12,000 feet. At 12,000 feet, the air is a lot thinner, which means that every rotation of the propeller means that it's moving a lot less air, which means it's creating a lot less lift, which means that the airplane was very mushy. Every control change that I made, going left, going right, using the remote, the drone was very slow to respond and just flying very differently than it did at lower altitude. In terms of altitude, I want you to think about flying at sea level versus flying in Denver, for example, which is a mile high. I live in Prescott in Arizona. We're about the same altitude actually as Denver, and the performance is greatly reduced. I also want you to think about you as a human being. If you do any kind of exercise, if any of you have ever gone to higher altitude on a hike maybe, or just even walking around, then you know that your body needs a little bit more breathing in order to respond to the same things that you would do at sea level. So if you were to do a run, for example, at high altitude, then your body is going to need a lot more air in order to perform, just because of the altitude of the pressure changes. Well, the same thing is going to be true with your drone. The performance are going to be reduced. The same thing is true with temperature and humidity. As the temperature increases, the performance of the drone is also going to decrease, and also as the humidity increases, the performance is also going to decrease. The worst possible scenario is going to be a hot, humid summer day. I used to live in Florida before I moved to Arizona, and hot summer days, I can tell you, happen all the time. So your performance, even though you're at sea level out there, your performance is going to be diminished by the humidity and by the temperature. Another thing that I want to mention is the cold temperature on the opposite side of the spectrum, the very cold temperature. If you're flying in the winter, the battery performance is going to be affected. It's different than the engine performance, than the motor performance, but your battery is going to have a much shorter life because of temperature. So you have to be careful with that. The last factor that is going to have a major effect on the performance of your drone is going to be the weight of your drone. A heavier aircraft means that you need more lift to get off the ground. Also, what it means is that more lift is going to be usually achieved by going at faster speed. If you have a fixed wing aircraft, faster speed means faster forward speed. If you have a quadcopter, then it means that faster speed are going to be achieved by faster rotation of the propeller. On the fixed wing as well, more lift means that you have a higher angle of attack. All of this, faster speed, higher angle of attack, just basically means that you're going to be creating more drag, which overall is going to reduce performance. Drag is not really something that we want to have. Reduced performance means a longer takeoff and a longer landing distance. It also means that our climb performance is going to be reduced. That's true for quadcopter, and that's also true for fixed wing. It just overall means that the engine is not going to perform nearly as well. A few other factors that you need to consider before you fly is going to be outside factors, I'm going to say, environmental factors. The runway or the launch area in which you're going to be. Now, if you're flying a quadcopter, that's not so true, but if you're going to be flying something that's going to roll and need speed in order to take off, then the type of surface that you have is going to be very important. Also, any kind of slope is going to be very important. Now, slope is true also for quadcopters. When you take off, you want to be on a level surface, because if you're not, if the drone is banked like this a little bit, as soon as you take off, one side is going to go up and then it's going to go up in the air, which is not really something you want to do. It's going to make it a lot harder to land as well. Another thing you want to pay attention, again, fixed wing or quadcopter, same thing, is the surface wind. As soon as you take off, the wind is going to be blowing you from side to side. Or if you're flying in a fixed wing, then as soon as you take off, you want to take off into the wind to get that additional airflow moving in there. Remember the relative wind? We want that additional air mass hitting the wing in order to create more lift. And then the last thing, this is true for everyone flying out there, is obstacles. You want to be careful with obstacles and make sure you have enough performance to clear the obstacles before you get to the obstacle, right? On the test, this is by no means all the questions that you're going to all right, this is it for this presentation. I want you to go over some typical FAA questions so you can see what's going to be on the test. This is by no means all the questions that you're going to find. This is just I picked a few that are representative of what's going to be on the test. When you're done with this, go ahead and take the quiz. That's going to give you basically all the FAA questions that I know of that are going to be related to this topic. I recommend that you don't move forward until you get at least 80 or 85% on the quiz, just to make sure that you understand this topic. And then when you're done with that, just move on to the next section. The first typical FAA question: to ensure that the unmanned aircraft center of gravity, the CG, limits are not exceeded, you're going to follow the aircraft loading instructions that are specified in what? If you remember when we talked about this, first off, B is not correct. The Aeronautical Information Manual, we haven't even talked about this yet. It is a real document. The Aircraft Weight and Balance Handbook, there is no such thing as this document. So the question is A, which is the Pilot Operating Handbook and the US Flight Manual. The term angle of attack, we've talked about this very early on in this presentation, is defined as the angle between, if you remember, it was the angle between the chord line and the relative wind. So answer A in this case. By the way, as you go through these presentations, these questions, I'm going to go through. I'm not going to wait for you to find the answer. So just pause, formulate the answer, find the right one for you, and then play again so you can hear the correct answer. When operating an unmanned airplane, the remote pilot should consider that the load factor on the wings may be increased anytime when. Well, let's take a look at the answers. The CG is shifted rearward to the aft CG limit. Well, we didn't really talk about the CG location and the load factor that doesn't really have much of a relationship. The gross weight is reduced. Now that wouldn't be true. As the gross weight is reduced, then the amount of lift necessary would be less. It's not really related to any of this. Answer B, the airplane is subjected to maneuvers other than straight and level flight. Remember, you're sitting in at Disney in one of the rides, and then you go down, and then all of a sudden you get to the bottom and you go back up, and then you feel all that G-force right here. Well, that's what it's talking about here in B. So B would be the correct answer. The angle of attack at which an airplane wing stalls will do what? Well, let's look at the answers. Increase if the center of gravity is moved forward. When we talked about the angle of attack and stalling, the one thing that I mentioned was that the wing is going to stall when we reach the critical angle of attack. Okay? I never at one point I talked about the effect of weight, which is answer B. Never I talked about the effect of center of gravity on stall. The only thing that I said is it basically stalls at the critical angle of attack. That critical angle of attack is not related to weight. So C is actually the answer here, remains the same regardless of gross weight. If an unmanned airplane weighs 33 pounds, what approximate weight would the airplane structure be required to support for a 30-degree bank turn while maintaining altitude? Now you have the figure right here, and the figure says for 30 degrees it shows as a load factor of 1.154. If the airplane is 33 pounds, 33 times 1.154 is 38 pounds. Closest answer is 38 pounds. A stall occurs when the smooth airflow over the unmanned airplane's wing is disrupted and the lift degenerates rapidly. This is caused when the wing does what? I've said the answer in the previous question. That happens when we reach the critical angle of attack. Critical angle of attack. Next up is regulation, so I'll see you there. It's kind of a boring and dry section, but I'll do my best to make it entertaining.